All right. Thank you for coming. And just to make sure that like everything is still working well, you can see the pointer here, right? Any
Yes. Yeah.
Okay, great. I'm going to start by just doing a very quick review of what we talked about last time. Um, and then afterwards, we are going to just like look at more examples and seeing different properties of different posets and also like learn about the rank generating function and things like that. All right, so last time we started with the definition of what is a poset. Poset is just um, a partially ordered set, meaning that a pair with a set and then an order that satisfy three conditions where you have to be reflexive, meaning that X has to be comparable with itself, and also we sometimes write X less than or equal to X for any elements in your set. Is anti-symmetry. So if X is less than or equal to Y and Y less than or equal to X, then X and Y are equal. And also, if you have three things that X is less than Y and Y is less than C, then X is less than C, so you get transitive. And for notation, it's not always writing less than, it's just like what we usually write. Like if we have the equal sign, then it means it is possibly to be equal. But then if I don't write it, then I mean that like they are not equal. And then I can also write in the opposite direction. They mean the same thing as we use our bigger than or smaller than like that. Um, and then why do we call it partial? Because not every two elements can be compared just based on these three axioms. And if two elements in a set can be compared, then we call it comparable. And then if you have two things that sometimes you cannot compare, then we just say that they are incomparable. And we also have this notation that we would talk about quite a lot is that what is the meaning of covering relation? So a covering relation means that X and Y can be compared, but there's nothing in between them. So in this case, then that just means that like we'll use this notation with a dot inside, meaning that they're directly above or below one another. So that's the meaning of that. And then if you have a poset that you realize that even like you just randomly choose two things and then any two things would be comparable, then we say this partial order set is actually a totally ordered set. So this is a total order. So example of like partial order set, or like I'm going to say poset all the time now, but like examples of poset that are totally ordered set are our usual number system. So we can compare any two numbers, like real numbers, rational numbers, integers, positive integers, and so on. Like those are like totally ordered set, and also they are infinite, right? Um, and in other, like if you want a finite, like a finite version, one of the example is that you can look at the set 1 to up to n, any n that you want as long as it's positive. And usually we use this notation to write it. And then use the usual ordering. Then of course any two positive integer can be compared. So it is also a totally ordered set and is finite in this case. We talk about, I'm going to again run through this list because we are going to use these examples today. So just a reminder of what we talked about last time. All right, we talk about Boolean algebra, which is like, okay, the set of elements that we want to compare are the subsets of n. So this is the power set of 1 to n. So and then like the comparison is the subset. So that's the Boolean algebra. And before I move on to all the lists here, just like to give you the examples here, we talk about Hasse diagram. Basically, your elements are the vertices, and then we draw a line between two vertices if one covers the other one. So, for example, this is the Boolean algebra, like on the three elements, so 1, 2, and 3. So you can see that the subset of 1, 2, 3 of this set 1, 2, 3 are the empty sets 1, 2, and 3, and then size 2 subsets, and then itself, right? So then you can see that like, okay, 1, 2 is a subset of 1, 2, 3, And there's no other sets in between 1, 2, and 1, 2, 3 using the comparison, like the inclusion comparison. That's why we have a line here. We don't have a line here because even though 1 is a subset of 1, 2, 3, but you do have another one that is sitting inside, meaning that 1, 2 is above 1 because 1 is inside 1 and 2, and 1 and 2 is inside 1, 2, and 3. So therefore, we don't have this line here. So in general, this type of diagram, you will never see a triangle because if you have this and this, then by the transitivity, we already know that this one is like gifted, right? Like, so this must be less than this. So when we draw the Hasse diagram, we only use edges when they are like a direct, like we call covers. So we only have covers. Another thing that we also talk about the Hasse diagram is that even though we just draw like a normal graph, it is actually a directed graph. All the lines here is secretly pointing upward. So they do have a direction. And this direction is going to be important when we talk about whether two posets are the same. But anyway, so these are the two examples that we talk about. This is the total order. So you see that's the straight line. And then here, this is the Boolean algebra on 3 elements. All right, so go back here, the list of things that we talked about last time. Dn here means that like n is an integer. And then so Dn is the set of all the divisors of n. And then when you compare two numbers, a is less than b if a is a factor of b. So for example, here, the 90 that we talk about. So you can see that these guys are all the elements, all the factors of 90. And then we arrange in such a way that like you can see that, for example, 18 is bigger than 9 because like when like 9 is like 9 is a factor of 18, and then when you divide it, like the quotient is 2, so that's impossible to have another number in between that it is a factor of 18, but this is a multiple of 9, right? So therefore, actually, in this case, all the edges here, the covering relation here is that the quotient is a prime number. So you can see that, like, for example, if we choose the 10 and the 30, here the quotient is 3, is a prime, and therefore you have a line here. So you can like order things like this, and you can draw a Hasse diagram of this poset. So that's another poset that we talked about last time. So that's the Dn. In this case, it's D90. We talk about pi n here. And what is this pi n? N is a number, any positive integers. And then so pi n is the set set partitions of n. And we say two set partitions, like a comparable in this way, b is less than or equal to b prime, if every block in b is in some block in b prime. So for example, this is a set partition of the sets 1 up to 9. So you can see that I have 4 blocks, 1, 2, 3, and 4. And then this is also a set partition of 1 up to 9. And then, but I have 2 blocks. I have this block and this block. And you can see that 137 is in this block, 2 is in this block, 4, 6 is in this block, and 5, 8, 9 is in this block. So therefore, you can compare them. So that's the comparison. And so we also drew it out. And this is an example of 1, 2, 3, 4. That's the pi 4 here. And if you have the set 1, 2, 3, and 4, and you want to do a set partition, so you can see that like, okay, well, you can either have 4 blocks, so each block has 1 element, or you have 3 blocks, so that would be one block with 2 elements and then 2 other blocks with exactly 1 element. So we have these 6 possible cases. And then you can have 2 blocks, and then 2 blocks, either you can have 2 elements or you can have 3 1 elements. In this case, there are 7 of them. And then like the relation is, say, for example, you see this 1, 1, 3, and 2, 4, you have this line because 1, 2, 4, and 3 you can see like 1 is in this block, 2, 4 is in this block, and 3 is in this block. Every block here is a sub block inside the other block. So and then there's no other sub partition that you can put in between, and therefore we have a line here. So if you have time, you can sit at home and then like try to really figure out how to draw the Hasse diagram here. I highly recommend that. We also talk about something interesting about the pi n here. So the total number of, if you give me an n, the total number of subpartitions, so how many different ways that you can like put like 1 up to n into blocks, then that's called a Bell number. And it says on the OEIS A000110. The numbers are like this. It has a lot of interesting properties. So I highly recommend you to like look it up if you're interested in Bell numbers. And like, for example, it is like a binomial transformation of itself. And also you can see that when you look at the exponential generating function, it has a very nice property here. So there are some interesting, like there are a lot of interesting things about the Bell number when you count. So basically when you count the number of subpartitions of n. So for example, in here, the Bell number of 4 is actually 15. So this is 1 plus 6 plus 7 plus 1. And that's this 15 here. All right. And then the other poset that we talk about here is the composition poset. And composition is just a sequence of positive integers that sums to n when you have when we use this notation. And then when we say two compositions are comparable, like alpha is less than or equal to beta, if alpha is a refinement of beta. For example, you have this is a composition because it's a sequence of positive integer. This is also a sequence of positive integers. And then so this is less than this is because you can see that it's a refinement of this guy because you still have the 2. You kind of cut the 5 into 2 parts, 3 and 2, and then 4 into 2 plus 1 and 3. But if you just swap the 1 and 2 in this case here, you would not get a refinement because here you see 2 is the 2. And then there's no way that you can add things up like in this order, they will get a 5. So this is not, these two guys are actually incomparable. And so that's the composition poset. And then we also drew it out. So for example, the composition of 4, you just find all the sequence that add up to 4, and then you draw this. And then let's look at like, again, the edges. So for example, this is a refinement of this one, and then you cannot find any other sequence that refine this and also will be refined by this. And therefore that's like a edge here because this directly directly bigger than this one without anything in between. So this covers this. And so that's the composition 4. And then after we drew it out, we realized that, hey, that looks very, very similar and actually the same as the Boolean algebra. So, so therefore we talk about something called like a isomorphism, and we are going to talk about this like very quickly as a reminder, but just want to go through the list of example, 3 more. And we have this, so we have this S here. What is this? S is the disjoint union of all permutations. And then we say 2 permutations are comparable, sigma is less than or equal to pi if pi contains sigma as a pattern. So what does that mean? And we drew it out last time here. So you can see that, say for example, we have 1, 2 is directly so 2, 3, 1 is directly covering 2, 3, 1 covers 1, 2. Why is that? Because 1, 2 is a pattern, meaning that you want to have something like A and B such that A is less than B. So here we do have that because we have 2 and 3, which is in that pattern, right? And for example, here you do have 1 and 3 here in the pattern of the first one is less than the second one. Here, 2, 1 means that the first one is bigger than the second one. So for example, you have this guy, you have this guy because of the 3, 1, You have this guy because you have the free one, or so on and so forth, right? So and also it does not need to be continuous. So for example, this one is inside, like 2 1 is inside this one, not just because of free one, but also because of this 2 1. So as long as you have a substring that is a pattern of this guy, you have like a relation, you are comparable. So that's what this S is. And this is the first example that you can see that is infinite, because you can just go up. You can have S4, S5, and so on and so forth. The next level has 24 things, and that's why I didn't draw it out. And we also talk about partitions. Partitions are just like composition, but you have to be weakly decreasing. So instead of, like, for example, here, these guys are composition. But this guy is a composition, but not partition, because it's increasing. I want something that is weakly decreasing. So for example, this is good, this is good, this is good, this is good, and this is good. All these three guys are not good because they are not decreasing. All right. So decreasing guys, so decreasing compositions are partitions. And so when you draw partitions, we would draw the Young diagram, meaning that we use boxes. Here we use the English notation, meaning that here this guy is 3 1. We read the number of boxes from top to bottom. So here this is 4. This is 3 1. This is 2 2. This is 2 1 1. This is 1 1 1 1. So these are the five things that we said we like here. Like, remember these 5 guys. So correspond to these 5 guys. And then so you can write all the partitions here. You can draw the boxes out like this. These are Young diagram. And then how do we talk about the relation? 2 things are comparable if one is inside the other as a subshape. So for example, this guy is inside this guy, and this guy, obviously, because you can really find the corner, right? But then you cannot find this guy in here or here. So therefore, you don't have any like line or like a path to go from here to here. So that's called a Young lattice, or for now, it's just a Young poset. And that's another example of an infinite poset here. And then the last one that we talk about is the BNQ, which is all the subspaces of FQN. So for example, here, if we look at F3, 2, meaning that you are like a 2-dimensional. So F2 is like F3 here, the 3 is the like FQ. So here the Q is 3, and then 2 is just like at most 2-dimensional. So we want to look at all the subspaces of F3, 2. So of course you can have the subspace itself or the zero subspace, but all the dimension, like 1-dimensional subspace, are either 0, 1, 1, 0, 1, 1, and 1, 2. They are generated by these. They are all 1-dimensional subspace of every 2. And then you just draw the like the relation. And in this case, it's very easy, like because this is the biggest, the ambient space, basically, like the biggest space. So of course everything is inside there, and then this is the smallest space, and it would be inside every single subspace. So therefore you have this shape here. But anyway, so this is an other finite poset. And then so you can see like there are many different ways that you can compare things, right? Like so these are the examples that we talked about last time. Again, stop me if you have any questions. I'm happy to explain further. Okay, so here we talk about like, so remember when we look at these examples, we say that, hey, these 2 guys, the Hasse diagrams is exactly the same. So basically they are the same thing if I rename the vertex, right? So therefore, if we can show that 2 things, like if we want to say 2 like posets are the same, we have to just, like, one of the way to say that is if you can draw the Hasse diagram. If they are exactly the same, then you just say that they are the same thing, and therefore, like from now on, instead of thinking the composition poset and the Boolean poset are like different things, I'm just going to say that they are the same. So if I know anything in here, I know everything in here, and vice versa. So I'm going to just focus on the Boolean algebra instead of treating them as different. Anyway, but how do you actually prove something are like the same? If I don't draw out the Hasse diagram, or like in mathematical term, what does that even mean? Well, you have to find a order preserving bijection. So meaning that if you have these two sets, you want to say that they are isomorphic as a poset, what you have to do is saying that, okay, choose two things here. If they're comparable, like S and T are comparable, and then when you go through your map, and then you would be in Q. Those two guys, your image has to be like preserving the same order, and also vice versa. So that's the order preserving bijection. And then if they are having such a map, then they are isomorphic. And then we also talk about something called dual. So self-dual is, so what is a dual? A dual is just saying that like if X is less than Y in your original thing, then Y is less than X in your dual. So basically you just flip your symbol, or you flip the two elements. And so that's called a dual. A dual is not necessarily like the same as yourself. But to think about dual is very easy, because like you just flip your Hasse diagram. So self-dual, meaning that after you flip your Hasse diagram, you get the same Hasse diagram. So for example, this is the B3. If you flip it, you will get the same shape. So that just means that like B3 and B3 dual is the same. So that's why we call them self-dual. But in general, it's not always the case. And you can easily find the order preserving map, the order preserving bijection, by just using S map to the n minus S. And then you will see that you will find the order preserving bijection from B3 to B3 dual, and therefore they're self-dual. Actually, not just Bn. If you have n is the same, Dn is also the same. Meaning that, like, if you look at these examples, this guy, if you flip, of course, it's still a strict line, and so with exactly the same number of vertices, so they are the same thing. So this one would be the same as its dual. And actually, this guy, if you flip it, it also will give you exactly the same Hasse diagram. So that is also giving you a self-dual element, poset example. All right, so and that works for any n. Okay, so to prove that Bn and composition are exactly the same, has a diagram, the way to prove it is just say that B is self-dual, and then from the dual you use this famous map in composition, meaning that if you give me a set, I can give you a composition. If you give me a composition, I can give you back the set. And the way to do it is very simple. So for example, you have to tell me the n. So for example, n is equals to 10. You give me a set. To find the composition, you choose the first one, 3, so as your first element of your composition, and then you just do subsequent division. So basically, 4 minus 3 is 1, 6 minus 4 is 2, 7 minus 6 is 1, and then use your n, but use n plus 1, so 11 minus 7 is 4, and then you will get your composition, and then you can go back. The reason that we want n plus 1 is because we have to make sure that this guy is positive, because this is a subset in n. So if that just means that n can be one of them. If you use n minus ak, then you will have the possibility to get n minus n, which is 0, which is not what we want. And that's why n plus 1 minus ak is the right bijection. All right, anyway, so last time we proved that these two guys are isomorphic. And then afterwards, we realized that, oh, well, Hasse diagram seems to play an important role to understand the posets. So we drew out all the possible posets with at most 4 vertices. We realized that there are 1, 2 in the p equals to 2. We have 5 when p equals to 3. Like the vertex, you have 3 dots. And then if you have 4 elements, there are, I think, 16 of them. So, and then when you draw things out, there are different ways to draw things. But like say, for example, these two guys, they don't look exactly the same, but they are actually the same thing because you can think about moving this dot just like a little bit and then pull it out, and then you will get this kind of like a ribbon shape. Um, this and this are not, they are not the same. They are not isomorphic because like these guys are basically like a directed graph. So remember, all these graphs are like this, so pointing upward, and this is this, right? So you can see that they are not the same graph. So they are not the same graph here, and that's why like we can flip it. Sometimes you can flip this guy because like even if you flip, you get exactly the same thing like when you point it upward. So you have to be careful what is the same and what is not. But last time we just like drew all of these guys out. And then at the end of the last lecture, we also talk about like subposet. So when we talk about subposet, there are like many ways to talk about like if you have a graph and then you talk about subgraph, there are many ways to talk about a subgraph. And so it's kind of similar. So here, what do I mean by subposet? Well, there are basically 2 major type of subposet, either a weak subposet or like a induced subposet, kind of like a strong version. So the weak subposet, what does that mean? Meaning that, okay, you give me a poset P, I first of all just find a subset Q here. And then if 2 things are comparable, then in the Q that I make, then it has to be comparable in P. For example, here you see that like I have this A, B, this like A, B, and C here. I have this A, B, C, and D here. So this is a weak subset of this guy because anything that is comparable here is also comparable in here. Also, like it's not like just taking the edges. For example, you can see that A, B, C here is still a weak subset of this guy because A and C are comparable. And then in this subset, A and C are actually comparable. So you can think about if I have a path from an element to another element in my smaller one, and then I have to be able to do the same thing in the bigger element, and that is a weak subset. A refinement is a special type of weak subset when P and Q are exactly the same. And then induced subposet, that's the most important one. That's the one that when people write Q is a subposet of P, that's usually what they mean. So basically saying that like an induced subgraph, meaning that you have the subset of P, and then S and T are comparable in Q, is if and only if S and T are comparable in P. So that's the meaning of induced subposet. So for example, this is a weak subposet, but like of this guy, but this is not an induced subposet of this guy because if it is induced, I have to have all the things that I can compare. So in here, so this, if I have another line here, then that would be induced. Here, this guy is induced subposet of this one because like I cannot draw this guy here because they are not comparable in the original thing. So this one is the induced subposet. And now let's see what if I jump. So for example, A, C, B here is not an induced subposet. Why is that? Because B is comparable with C in here. So this is not an induced subposet. But if I change this guy to a D, then because like if you are comparable here, like just think about A, C, and D. A, C, and D here. A, C are comparable, C, D are not comparable, A, D are not comparable. So then this guy is capturing every like comparison in here if you just look at the 3 things A, C, D, and therefore this is an induced subposet. All right, so those are the things that we talk about. I see there's a chat. Okay. And all right. So, and the last thing that we talked about last time is here is saying that like, okay, well, if you have a poset P and is finite, then how many induced subposet can I make? And the answer is 2 to the power of number of vertices, because you just pick out your vertex, then you can easily know how to draw your edges. Therefore, this is the same as talking about like the sets of elements that you pick is exactly the like would be uniquely determining your Hasse diagram. Therefore, you just need to count the number of subsets, and therefore is 2 to the power of the size of P. So these are all the things that we talked about last lecture. Hopefully that gives you like a quick review of what we talked about. So now we can move on to some like why do I talk about subposet? Because there's a special subposet that we are going to learn about. Is called the intervals. So what is that? Well, an interval is basically just like you pick two things. If they are like, first of all, assuming that they are comparable, if they're comparable, then I want to find all the things inside P that are bigger than S but smaller than T. So that's the definition here. And you can have like different notations. You can have this open interval. You can have like open and close interval, like just like our real line. And if they are not comparable, then if S and T are not comparable, then that would be an empty set. Okay, so for example, you can have an open interval of S, and that's empty. You can have a closed interval of S, and then that's the singleton set S. So that's a special subposet. It's an induced subposet. Um, and then you will see something called locally finite. Um, so a poset is locally finite if all the intervals are finite. Okay, so for example, like we have these two things here. But if you choose two comparable elements and try to just find all the things in between the two elements, you can always really find a finite set. So even though they're infinite poset, they are actually locally finite. So locally finite just means that you can find all the intervals that you create from the P here, they are also finite. Also, that's a term that I probably would not use much, but I also want to just include for completeness, is saying that like, what is a convex subposet? A convex subposet is that like, if the interval AB in P is also in Q. So for example, this guy here, this is induced subposet of this guy because you can compare A and C only. But it is not convex, because convex means that like the interval AC, AD, and CD has to be the same interval as this guy. Well, AD and CD, they are not comparable, so like the interval are both empty set, but the AC interval in P is actually like containing A, B, and C, while the interval AC here does not contain the B, so therefore this is not a convex subposet of this guy. All right, so therefore all intervals are convex inside P. All right, so to talk about the intervals, because we are going to learn about like chain and like rank, we have to make sure that the notation is clear. So I'm going to just like give you examples. So here, let's look at the D90. And I want to look at the interval 2 and 45. And so like look at this 2 and 45 here. So we want to see like, okay, well, is there anything that like uh is in between 2 and 45? Well, what do you think? Is there anything in between 2 and 45? All right, so the answer is none because like 2 and 45 is not comparable because if you have to be compared, like if you can compare two, like if you want to compare two numbers, one has to be a factor of the other one. So they are not comparable, therefore that's an empty set. All right, so how about the 2 and the 18? Well, first of all, this is like not empty now this time because 2 is definitely a factor of 18. And then you just look at the Hasse diagram. Um, 18 to 2, like just record all the things in between 18 and 2. And in this case, you only have one. You only have this. So that just means that this guy is 2, 6, and 18. And how about if I have 5 and 90? Well, let's see. 5 is here, 90 is here. Anything in between them are like this. These are all the possible paths, right? From 5 to 90. And so you can actually write everything. So it's 5, 10, 15, 30, 45, and 90. Okay, so that's interval. Okay, so interval does not mean that you only have one line in your Hasse diagram. It's everything that is in between the two things that you can compare. And you can see that they actually form a subposet itself, and it is convex. So you would not miss any element. All right. Okay, so how about the other examples that we have? For example, if you have a chain, the like 1 up to n, and then if I want to say like find the I and j, so basically it's the same as the interval, like the same as the set j minus I, right? Because like say for example, if I have 1 up to 100, and I ask you what is the interval of 4 and 15, well, that would be like 4, 5, 6 up to 15, obviously. And so that's the same as 1, 2, 3 is isomorphic to 1, 2, 3 up to 12, right? So this is basically oh sorry, j minus I plus 1 plus 1. Right, so that would be just like your 15 minus 4 plus 1 here, right? That's that's the 12. And then so how about Bn? With in Bn is the Boolean algebra. If you have two sets in the Boolean algebra, and then I want to know what is the interval from S to T, it's actually the same as the Boolean algebra of the size of S minus T. Okay. So oh sorry, T minus S. T minus S. So for example, this is too small as an example, but like say for example, this guy is the B3 and I want to know the interval from here to 2, then that would actually just be this one, right? And this is actually the same as the Boolean algebra B2. And the 2 is just the number of elements from 1, 2, 3 minus the 2. Okay. And then how about the D90, like this guy, right? So how do I know like how to find the interval? So the interval say M and L, so L and M here is isomorphic to D and then M divided by L. If L is a factor of M, meaning that here this guy that we just drew here is isomorphic to D18. And why? Because you can just divide everything by 5, and then you would get like 18, and then 6, and then 9, and then you will get 1 and 2 and 3, and then you have this guy, right? So that's isomorphic to D18. So the interval itself, you can see that they are also a subposet. Um, Last example, like if I have the set partitions of n, and then I have some set partition, and I know that this guy has k number of blocks, then the interval from this to the top element is just everything, like you have exactly one block, is actually the same as pi k. So basically what I'm saying is that, like, say for example, go back to this example, and then like if I know that there are here I have three blocks, and then I want to know this to this, the interval will be here, 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 here. And this guy here is actually the same as pi 3. So that's the idea. Okay. So that's intervals. Any question? All right. And then a new term that I'm going to talk about is maximum element. So first of all, what is a maximal element? So what is a maximal element? M in P, so it's an element inside your P. Maximal means that you cannot find anything bigger than it. So no T in P such that T is bigger than M. Okay. So that's maximal element. Minimal element is basically the same idea. M inside P, so you cannot find any T in P such that P is less than M. Okay, so that's easy. Now, but what is maximum element? So maximal and maximum are not the same. So maximum element, we usually use one here. It's an element in P if it exists. So one is bigger than everything. So if you can find if you can find something that is comparable to every single thing, and it's always bigger than everything inside a poset, then we call it the one. And if it exists, it must be unique. You cannot find two of them, because if you have two of them, and then by definition, they have to be comparable with each other, but then they also is bigger than each other, so there has to be the same guy. So therefore, that's exactly one of them. Same idea of minimum element. So we usually use 0 to denote it. So the minimum element is going to be smaller than or equal to every other thing. And again, if it exists, it has to be unique. And now, so how do I know, like if I look at a Hasse diagram, is it always true that I will have a maximum or minimum? Well, if it is finite, you still may not be able to find these guys, but you will be able to find these guys. So let's see. Let me give you an example here. So here, like, let's look at this one. 4 elements. We saw it as an like example of the Hasse diagram. Even though I drew it like this, you can see that these guys here are actually maximal elements, because nothing is above them, right? And then these guys are minimal elements because nothing is below them. So they are the bottom. But you don't find somebody can compare with everyone. So that's no maximum and no minimum. No maximum and no minimum element. So you can see that it's not like where you draw it, because even if I draw it in the bottom or the top, it does not really affect whether it is a maximal or minimal. It depends on whether you have a line above or below. Um, and like an element can be both maximal and minimal. And a poset can have maximal and minimal elements, but it does not necessarily always have a maximum or minimum element. Right? But if you have a maximum, then it must be maximal, right? And then 0 is minimal. All right. Okay, so we have all this terminology. And then now the next terminology that is important is called chain. Okay, so what is this? This is a totally ordered subposet. Okay, so therefore you can find something that are total, like it's basically kind of like a line on your Hasse diagram. Any two things can be compared. And then for a chain, there are two types of chain that's coming called maximal chain. Maximal chain. Okay, what is a maximal chain? That's a chain, of course, um, that is not properly contained in any other chain. So basically saying that like, okay, no other chain would be bigger than it, right? So it is the maximal. All right. And then that's another kind of similar, but not exactly terminology called saturated chain. Okay, so what is that? So if I call this chain C, so for any S that is directly less than T in chain C, there does not exist any other element outside this chain such that S is less than U less than T, such that C in U is a chain. Okay, what does that even mean here? Well, it's just saying that, okay, if you have S and T, they are comparable. And then a saturated chain in the C. So C may be like something here. And then because it's totally ordered, so that would be some line, right? So that's your chain. And then like this line here, it's something S and something T, and say T is bigger than S, you will never find something outside this chain U such that if you join everything here, it will still make a line here. Okay, so that's called saturated chain. So how does that work? Like, what is an example? Okay, so let's go back to this guy that we have. Let me just copy and paste off of D90. D90 is a good example. Copy and then go back. Okay. So for example, let's find a saturated chain. So this guy here is saturated. Why is that? Because you cannot find any number here that like say for example, there's no number that's in between 2 and 6. There's no number between 18 and 2. There's no number between 18 and 6. So that you cannot find any number here that is comparable and still make comparable with all three of them. So this is saturated. Okay. However, this is not maximal because you can find another chain that could probably properly contain it, because this is a chain, right, that we can contain this saturated chain. Right? And then Now, what is a chain that is not saturated then? Well, let's see. If I have 1, 10, 30, and 90, okay, so let's see what they are, where they are. We have 1, 10, 30, and 90. This is a chain, right? Because even though you don't like, you do have a way to go there, right? These things, any two of them are comparable, right? Just pick any two numbers, you can compare them. So this is a chain. However, it's not saturated because you can find another guy outside these four numbers, namely 5, and then you can make another chain. So you can make this chain here, right? So therefore, this guy is not saturated because you can actually make it longer by inserting another number. So this is not saturated and not maximal because if you can make another bigger chain, then that bigger chain must be properly including your this chain here. So therefore, not maximum. So if you are maximal, you must be saturated. It's just that if you're saturated, you may not be maximal. So you have this relation here. Okay. And then if you are locally finite, so let me just write it here. In a locally finite poset, all the chain must be of the form, sorry, all the chain that's saturated. So T1, TK is saturated if and only if all these like relation here is covering relation. So that's how you can see it's saturated. And that's good because that's exactly why Hasse diagram is powerful because you know that's a saturated chain. And if it is locally finite, that just means that I can find a path that are all actual lines, right? Then that's a saturated chain. Like you can see that this is not a saturated chain because I don't have a line directly from 10 to 1, right? So, but I do have this path here, then that's a saturated chain. Okay. So Hasse diagram is usually your friend when you're looking at poset and then look at this property, but of course there are much, much more that we can talk about. All right, so now like we look at chain and chain is like obviously an interval. It's just like, well, a chain is not, it's not, sorry. A chain is not an interval, but a chain is like a totally ordered set. So it's basically a path, just not say interval. Make sure that you don't make the mistakes because like the interval of say for example 90 and 1 is everything, right? But if you're a chain, you have to tell me exactly your path, the way that you go from one to the other. Anyway, so now any question? Is that clear? All right. So now we talk about the length of a chain. Okay. So a length of a chain C is just the number of paths, the number of lines. So, or the other way to say it is the number of vertices minus 1. All right. So for example, the chain, this chain here, the length of it is 3. Why is that? Because you look at that's like 1, 2, 3. So that's like 3. Or you can say 1, 2, 3, 4 minus 1 is 3. Okay. Now, finally, we can talk about rank. Okay. So what is rank? So the rank of a poset, P, is the maximum of all the length of the chain in the poset. Okay. So so you just basically look at all the chain, but as we already know that like there's a notion of maximal chain. So instead of looking at all chain, you can actually also look at just the maximal chain. Because if you are not maximal, meaning that you are already contained in an other longer chain, so your length must be shorter. So instead of looking at all chains, you just need to look at all the maximal chain. And we will also talk about, like, sometimes we'll use this notation. I know that I use L of like a chain, but like I sometimes would also look at the length of X and Y in a poset. Why, like, what is that? This is actually the rank of the subposet XY. And then so this is the same. Like, I'm just trying to tell you that in some notation, when you have the length of a chain versus a length of two elements, a length of two elements is just saying that, okay, if these two guys are comparable, they will give you a subposet and then the interval. So basically like XY is an interval here. And then so you have a subposet, and then if you have a subposet, then you can talk about a rank. Okay, so that's kind of like a abuse of notation. Anyway, so we talk about the rank of a poset, basically talking about the longest length of a chain. And that's the starting to have some fun thing. So if every maximal chain in P has the same length n, then so basically it's saying that, okay, when you're trying to find the rank of P and then you look at all the maximal chain and you realize that you don't have to do any comparison because every single maximal chain is the same thing. In that case, then we call that P is graded. And then we say it's of rank n. And then there is a unique rank function. So you can find a unique function row from your poset to 0, 1, 2, up to n. And it's a surjective map. And we call it a rank function such that row S equals to 0 if S is minimal. And row Y equals to row X plus 1 if Y is covering X in P. Okay. And then we usually say like, S has rank I. So far I define rank for a poset, but you can also say the rank of an element if your poset is graded. So the rank of S is basically kind of like the height of it. So it would be of rank I if row S equals to I. So if the rank function tells you that it is the ith level, then that's like rank I. Okay. So to link it back to this like notation that we talk about here, actually, if you have like the row is well defined, meaning that your P is graded, then if X and Y are comparable in P, then we will also generalize our notation of row. Row XY is actually the same as the length XY. We will define it as row Y minus row X is actually the length of XY. Okay. So that's the relation between all these notations. All right, so that's the rank. And so I know that I have around like maybe 10 minutes. So I will give the examples of all the rank, like look at all the examples that we have and then see if they are ranked, like they're graded. And then if they are graded, what is the rank of the poset, and also like if they have zeros and ones and etc. So let's go through this guy. Okay. All right. So we learn about rank and then we talk about graded. So let's think about let me use blue color, meaning that whether it's rank or graded. Is this rank? What is the rank? And then is it graded? Okay. So and also whether it has 0 and 1. Okay, so let's see. So this guy, it has the 0 element and it also has the 1 element. And or just the 1 element in this case. And this guy is obviously rank 0. And then it is also graded because you have exactly one thing. All right. Okay. This guy has no 0 or 1 because you cannot find an element that can compare with every other element because that's one of the property of the 0 and the 1. And so like you don't have that. While this guy you do have that. So this guy you can easily see that this guy is 0 and this guy is 1. Okay. So now is it like what is the rank of this guy? This rank is 0. Oh, sorry. This rank is 0 and this guy the rank is 1. Okay. Remember what's rank? Rank does not mean graded at all. Rank is just saying that like find the longest chain. So this longest chain is 0, this longest chain is 1. So let's just do all the rank here. So here longest chain is 0, longest chain is 1, 1, 1, 2, right? So that's the longest chain. And then here 0, 1, 1, 1, 2, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2. Oh, sorry. Yeah, 2 and 3. Right. So you can find the rank of all poset like that. But are they graded? Meaning that is it true that all the maximal chain has the same length? So for example, here, this guy is graded because this is the chain, this is the chain. Um, these three are chains itself, like this is a chain, this is a chain, this is a chain, all of them of the same length. So this is graded. This one is not graded because this is a chain itself, like maximal chain. And it's not the same length. This one is true,
But it
this
still
one is
has
true.
that example
Sorry.
still has a unique rank function, right? So it's not
Mhm.
necessarily you can be non-graded and still only have a unique rank function, right?
No, so if you are graded, right? If you're graded, then you will have a unique rank function. But here you cannot, right? Because you can give this guy of rank 0 or rank 1,
I thought it had to be 0 because it was minimal.
or is also maximal. What if I draw it a little bit higher?
Well, um, I see.
Right. So it's not the position that you draw it. Like these guys, I can draw it anywhere, right? So I can also give this guy
Oh, so it's,
like
it's not minimal or maximal. Uh,
no, it's just actually minimal and maximal because minimal, the definition of minimal is saying that there's nothing below it, right?
right.
And this guy, nothing below it. Is it
But
maximal? Minimal, meaning that
didn't your
there's nothing.
condition need minimal
Mhm.
ones to be 0 though?
Um, no, so this guy is like if it is um like if it is graded. So this function
Oh,
is
if it's
only
graded, then you can.
right.
Okay.
Right. But the problem is this guy is not graded. So I cannot find a unique rank
I see.
function.
Okay, so what you're calling a rank function is just a function from p to the numbers, and then you're saying if it's graded, then it can have unique
Right.
with these properties. But then you're seeing, oh, well, I have a function. Okay, I see now. Thanks.
Right. So I mean like it doesn't mean that like I mean if you have a unique rank function then you can see that why it is graded. Um satisfying all these conditions. But in this particular case, It's just saying that because like all the maximal chain are not like the maximal chain are like here and here, so it's not really like it's just not graded in this case. Does that make sense? I'm not sure if I
No,
explained it
it
correctly.
makes sense now. Thank you.
Okay. So here you can see that this guy is obviously graded because you only have one maximal chain. Um, every maximal chain here has the same length 0, so therefore this is graded. This is not graded because you have all these guys here. This is
Here,
not graded because of this guy, not
uh,
graded. Mhm.
uh, uh, so the rank function is only defined for comparable elements. Yes.
The rank function comparable. No, so the rank function. So say for example, if you're graded, right? If you're graded, say for example, this guy is graded, then I just need to know that, okay, well, what are the minimal guys? These two are minimal. I'm going to give it 0. And then this guy is maximal. I'm going to give it a 1. Well, not maximal, sorry. Like it covers it. So that's why I give you a 1. So for example, here, this guy is the minimal. Uh, is a minimal guy. So I call the rank function of this guy 0. This is covering this, so that's 1. And then this guy is covering the 1, so I add 1 to it, so that rank is 2. Does that make
Okay.
sense?
Yes. Yes.
Yeah. So so that's how the rank function comes in. And here again, not graded. And then this one is graded because you only have two maximal chains here. Um, and then this one is graded. This one is also graded. This one is graded. Oops, graded. And then this one, is it graded? Yes, because maximal trains are here or here. So therefore that's graded. Fibbit, of course, is graded. Okay, this guy is not graded because you have a chain of length 2, maximal chain. You have a chain here of length 1. So therefore it's not graded. And if you flip it, of course, still not graded. This guy is graded and this guy is graded. All right. So the idea of graded is basically saying that you can easily find, like you can have like level 0, level 1, level 2, and then you know exactly where to put your guys. And here I like say for example, this guy I cannot because like I have these three things. I can easily put this as 0 and I put it as 1. But I don't know where to put this guy because like putting up or down it seems to work. And so I cannot really give it a height. I don't know where it lives in. So a greater thing is like really nice because your Hasse diagram would have levels. So for example, all the things here, like these bigger examples, you can see that like nicely we have all discrete. Like all these guys, like you can see that like if you're level 1 from below, you have exactly one line to go there. Here you can easily see that they are level 2 because you have like all these chain, right? Level 2. Every path has exactly 2 edges. Like for example, from 30, how do you go to 30? You can go this one, you can go this one, you can go this one. You can see that everything has 3 lines. So you can easily put it at level 3. And then same thing, level 2, level 1, and so on. So for example, in here, you will see that level 1 are all the things with like they are prime factors. If the top level -1 are always the things that when you do the division and then the quotient is a prime number. So that's the idea. Um, so that's the rank. And so you can see that like all the things that I drew out are actually graded and finite. So that's the rank of a poset. Um, and I think I am over 1 hour. So maybe that's a good stopping time because next time So now that we understand what is a ranked poset and like the rank of an element, then I can talk about what is a rank generating function. So it's kind of like a spoiler of what we are going to talk about next time, which I really like, is the rank generating function. How do you define it? We usually call it FPT. And this is just saying that I from 0 to n, where the number of elements of rank I, and then t to the power I, where here n is the rank of p. Okay. So, or like we are going to study the rank generating function of all these guys that are graded and all the poset, and some of them has really really nice beautiful things about them. And next time I'm also going to talk about how do you get new posets out of small posets, and that is going to give you something called like parallel, I think it's series parallel poset, which is like important in like machine learning as well. So those I'm going to talk about next time. But again, I'm going to use all these things as my running example. So if you're planning to join the next one, I would highly recommend you to like look at all these examples, especially like these things, and also of course these things. All right, so I will stop here. If you have any questions, feel free to ask.
Thank you, Anna. That was very nice. I can stop the recording and then we can take some questions.